Okay, let's get started, please. So can anybody tell me what we're doing? Anybody remember what we're doing?
Properties of logarithms.
Properties of logarithms, right? So we're, right, the exponential function and the logarithm function are our first encounters with so-called transcendental functions. And so, it turns out that, like I said before, exponential function is considered to be the most important function in mathematics. Its inverse function, the log, has a bunch of useful properties. So it's kind of a, these are super important functions. So properties of the log, right? So there's this first property that when you take the log of a product, you can just take the sum of the logs, right? And if you take the log of something to a power, the log of x to a power, then that turns out to be that power times the log. Okay. So historically the log was used for people as a way for people to calculate things more easily. So like if you had you'd have this tape, you'd have a book of logs actually, and you could say, okay, I want to know the product of something, and you could look at the logs. You could sum the logs of the things that you wanted to take. You want sum the logs of the factors, and then look in your log book and say, okay, that corresponds to what number. So it was a way of actually doing calculation. So like before calculators, I guess. So in fact, when I was a kid, my dad gave me a book that was just full of logarithms. Just a book of logarithms. Also a book of it also had like square roots and stuff in it. So like pre-calculator. Was I born before calculators? I don't know. Anyway, so in any case, I had such a book as a kid and enjoyed it. Okay. Okay. So let me just say one thing about these things. So why are they true? Right. Why are they true? Why are these properties true? Well, we saw that what you can do to verify them is just to hit them with the exponential function, right? So this statement being true, right? For this to be true is equivalent to asking, is it true that e to the log x to the y equals e to the y log x, right? So remember, we had this thing that, to verify, if you want to check that a equals b, that's equivalent to checking if e to the a equals e to the b, right? We said that, we mentioned that last time. Okay. And so, so is this true? Well, what's e to the, let's say that these are log base e. Okay. What's e to the log base e of x to the y? Take 1 minute and see if you can evaluate this, and see if you can evaluate this. And chunk. Okay, talk with the neighbor for a few seconds, please. So Okay, what's this thing on the left? E to the log base e of something.
It's just that something.
It's just that something, right? Because e to the x and log base e are inverse functions, right? So it's just going to be that something, right? Right? E to the log base e of whatever, right? These just cancel each other out and you get x, right? Okay, what about on this side? This one is a little bit trickier, but you can use properties of exponents. Okay, right? What do you know about exponents? If I have e to the a times b, what's that equal to? You have some properties of exponents that maybe you remember from childhood. What is this? Reason.
The A log.
I just want properties of like if you have like 5 to the 2 times 5, can you rewrite that in some way? 5 to the 2 times 7. Just yeah, Olivia.
It's 5 to the 2 plus 5 to the 7.
No. No. No, I think you're mixing up something. Zoe?
It would be 5 to the 2 to the 7.
Yes. Right. Remember this? The product. This is something to the power 2, and then you take that to a power, and then you multiply the exponents, right? Or you could do it in the opposite order. This would also be 5 to the 7 to the 2. Right. So let's come back over here, right? And so we've got e to the blah times blah. Right, so I'm going to rewrite that as e to the log base e of x quantity to the y. Right? Right, so something to a product is just going to be something to the factor quantity raised to that other factor. Okay? Right? And what's e to the log base e of x? Olivia?
It's what I just said.
X, yeah, what you just said. They cancel each other out. Right? So you get x to the y. Right, so this is also going to be x to the y. Okay. So our question was, is it true that these two things are equal? Well, yes, because this is basically equivalent to the statement, is x to the y equal x to the y? And that's true. Right, x to the y is equal to x to the y. This is equal to that. Okay. Yeah, so the properties of exponents, right? The properties of exponents, like a to the xy equals a to the xy. This property of exponents gives you this property of logarithms, right? This property of exponents gives you this property of logarithms in an identical way, and we saw that last time. You guys okay? Everyone okay? Okay, good. Okay, so let's see. Let me do. So there's those two properties that I just erased. I'll keep them. Log xy equals log x plus log y. Log x to the y equals y log x. Okay, so let me show you an example of a kind of application of this. Last time at the end of class, we showed this example where we had a bunch of terms and then we combined them all into one term, right? Remember that? Okay, so now we're going to do the opposite sort of example. So I have like the natural log of x squared over 2x minus, x squared times the square root of 2x minus 1 over 2x plus 1 to the 3 halves. Okay, and so what we're going to do is just use these properties to simplify. Okay, right. And remember, this one has as a consequence, these two together give you that log of x over y equals log of x minus log of y. So that was like this consequence of these guys. It was a useful one. Okay. So one thing we could do with this is say, okay, well, we've got a fraction here, so we're going to take natural log of the top minus natural log of the bottom. Okay. Right. So we're going to expand this thing out into small terms. Okay. What could we do with this thing? Should we use the first one or the second one? First one or the second one at this point? Natural log of something. Yeah, still.
Maybe use the first one to just split up the x squared and the square root of 2x minus 1, and then use the second one to look at the exponents.
Exactly. In fact, we can't use the second one at this point because we don't have something to a power, right? We've got something a power times something else to a power, right? We could use it on this one, right? This is something to a power, right? So we could do it, we could say, well, look, by the second property, this is equal to natural log, 3/2 natural log 2x plus 1, okay, by property 2. But we actually can't use property 2 on it at this point, right? Everybody see that? That you cannot use property 2 here? Right. We can use property 1 because we do have a product here, right? So we use property 1, we say natural log of x squared plus natural log of 2x minus 1 quantity to the 1/2. Right. And as Stella said, now we can use the property 2. We can pull the 2 out, 2 natural log x plus 1/2 natural log x minus 1 minus 3/2 natural log of 2x plus 1. Okay. This is handy, right? You can take, something that, then we have got the natural log of something complicated. You can break it into combinations, sums, combinations of natural logs of the factors. And like we said last time what we did was we started with something like this, and then we combined it into something like this in the opposite direction. Okay. Okay. I want to. So there's one thing in that is introduced at this point that I don't think is that useful, but so here's a nearly. I think this is a nearly useless trick. But, here's something that you can do, which is change the base of the log. Okay. So here's an example. You have log base 2 of 5. Okay. Somebody wants log base 2 of 5, but your book of logarithms is in log base 10. Okay. Your book of logarithms is log base 10, and you say like, I need to express this in terms of log base 10. Okay. So what you say is that, okay, well, so change to log base 10 to expression involving log base 10. Okay. So what you could do is the following. You could say, well, this thing, whatever it is, I'm going to call it x. Okay. I'm going to call it x, and then I'm going to translate that to I'm going to move that to its exponential version, right? Remember, every logarithmic statement has an corresponding exponential statement, right? Okay. So take 10 seconds and tell me what the exponential version, write down what the exponential version of this would be. What does this say in terms of exponents? Turn to somebody nearby and tell them what you wrote. I hear a lot of correct whispering. Somebody want to say out loud, say more loudly what you're whispering? Anybody? What's the corresponding statement over here? Over here? Many of you have it right. I heard like at least 2 or 3 people saying it's blah 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 blah. Nobody wants to say it? Oh yeah, not at all. 2 to the x equals 5. Right. That's what this says. Right. Log base 2 of 5 equals x. That means x is the power you raise 2 to get 5. Right? X is the power. This is the power you raise 2 to get 5. Sorry. Okay. If you forget that, I often forget that. So if you forget that, it's what you should do is just exponentiate those signs. You just say, I'm going to take this to 2 to this power. I'm going to take 2 to this power. Right? And then use the fact that these guys cancel each other out. Right? 2 to the x and log base 2 of x are inverse functions, and so you just get it from there. Okay. So you can just exponentiate to get the exponential version. Okay. Okay. So, but remember what we're trying to do. We're trying to change this into something. Write this thing in terms of, write this thing in terms of log base 10. So now we're going to take log base 10 of both sides. We get log base 10, 2 to the x equals log base 10 of 5. Right? And we wanted an expression for x. We can use the second property, pull the x out. X log base 10 of 2 equals log base 10 of 5. Right? And that tells us that x is log base 10 of 5 over log base 10 of 2. Okay, so this thing we can rewrite as log base 5, I'm sorry, log base 10 of 5 over log base 10 of 2. Okay. Questions? Is that clear? Any questions? Yes,
Can
Manuel.
we go over like the last steps so we made log base 10 of 2 is equal to log base 10 of
So from here to here, you mean?
5? Yes.
I just divided both sides by this, right? So I've got x times this equals this. So I divided both sides. Maybe I didn't write it clearly enough. So I've got x times this equals this. So I got x equals log base 10 of 5 over log base 10 of 2. Okay. Just dividing, right? Like if you say that 2 times 5 equals 10, that's the same thing as 10 equals, 2 equals 10 over 5. Right? Just divide. Okay. Other questions? Okay, so we could have done this. So you notice that we could have done this with any change of base. So like if I have log base a of x, and I want to switch it to log base b, we could go through the same process and get log base b of x over log base b of a. right? So this is a general formula, right? We just do exactly the same thing, and we get this. Okay, so this is the formula if you want to switch from one base to a different base in the log, using the log function. Okay, but like I said, this is not that useful. Maybe it's a good exercise for you, but it's not something that you use very often, I'd say. Okay, let me just make one comment. If I have log of, say, log of the quantity to the 5th power, is that 5 times log of 3? No. So people sometimes, this is a kind of common, it's an easy mistake to make. We have this property, log of, something to a power. You can pull that power out, right? If you have log of something to a power, yeah, you can pull the power out, okay, because of the properties of exponents, right? But this is not the same. This is not the same thing. Right? This is log of a quantity to the b, right? So don't get confused between log of a quantity to the b and log of the quantity a to b. Just watch out. Okay. So that's all from section 5.4. Let's erase everything. Okay. Section 5.5 is called logarithmic, exponential, equalities, and inequalities. Okay, so remember, we noted before that you have this exponential function saying that, assuming that b is bigger than 1, the exponential function looks like this, and the logarithmic function looks like this. Something like that. That's actually not right. Logarithmic function should be slower, and the exponential function should be faster. But anyway, something like this. Okay. And we noted that these guys are one-to-one functions, so if a equals b, that actually is if and only if, if x equals y, that's if and only if b to the x equals b to the y. It's also if and only if log base b of x equals log base b of y, right? So we can take our equalities and then hit them with either of these functions, and we can just prove the other equality, right? This is great, right? This is a really useful thing, right? Because then we can solve equalities that we could not solve before. Okay. So, like the one that we did last time, the one that we did before was, I think, something like this: e to the 2t minus 5 equals 5,000, right? And we said, well, this is kind of hard to do by itself, but if we hit it with the logarithm, it's easy, right? So we said, instead of considering this one, let's hit it with natural log, we get natural log e to the 2t plus 2t minus 5 equals natural log 5,000. You don't have to copy this because we did this last class, right? You get, and then these guys cancel. You get 2t minus 5 equals natural log 5,000. And then you just solve for t. So that, right, so this is kind of a useful trick. Let's see. What if I give you something like this? Log base 6 of x plus 1 equals 1. Okay. Take 1 minute and see if you can figure out what the answer is. Okay, talk with somebody nearby. Okay, how should we do it? What move should we make? We've got a logarithmic equality, so we're going to hit it with the exponential function, right? So what should we do? Will somebody want to tell me what to do? Yes, Stone.
Raise both sides, like with these things.
Yeah, so this is a 6, by the way.
Oh, this is 6.
Sorry. I should make my 6s look different from my B's. Anyway, so take 6 to this power and take 6 to that power, right? So that is, pipe both things through the 6 to the x function, right? So we're going to get 6 to the log base 6 of x plus 1 and 6 to the 1, right? Those guys are going to cancel out, right? We used 6 because we've got log base 6, so those would cancel. We get x plus 1 equals 6, and so x is 5. Okay, right? So, simple example of how you can take, exponential equalities, get them with logs, and then make them into, equalities that where the thing you're looking for is no longer in the exponent, right? And here, the thing you're looking for is in the logarithm, so you exponentiate it and you pull it, you get it out of the logarithm, right? So you've released it from its prison or something. Okay. Here's a more complicated one: log base 3 of x plus log base 3 of x plus 2 equals 1. So you can guess, we're going to use some properties of log, now that we have them. Okay, turn to somebody nearby, talk with them about how you're doing it, even if you haven't finished. Okay, what should we do? Sort of, what's the first thing we're going to do? You've got logarithms here. Should we just, I don't know. Should we just exponentiate both sides, or do you want to? It's kind of up to you. Yes, Zoe.
You can combine them by multiplying x and x plus 2.
Yeah, right. Log. Remember, sum of logs is log of the product. Right? Log of the product is sum of logs. Sum of logs is log of the product. So we can rewrite this as log base 3 of x times x plus 2 equals 1. Right? And now we're back in this kind of previous case. Now we're going to run everything through 3 to the x. We get 3 to the equals 3 to the 1. Right? Okay. And if you know what you're doing, you don't have to write it out like this. You could just say, look, this is going to be 3 to the 1. Okay. So you get this x squared plus 2x is equal to 3. Then you get, well, actually, before we get there, let me say that we could have just as well run this thing through 3 to the x over here, right? If we do, we're going to get 3 to the log base 3 of x plus log base 3 of x plus 2 equals 3, right? And then you would use your properties of exponents, right? Properties of exponents say that this is going to be the product 3 log base 3 of x times 3 log base 3 of x plus 2, right? And then so you would get x times x plus 2 equals 3. Right? Either way, because like we said, this property of logs is basically this property of exponents. So either way, it's doing the same thing. Okay, in any case, we get to this point, and then we say, okay, look, this is going to be x squared plus 2x minus 3 equals 0. And what could x be then? What are the solutions?
Negative 3.
Negative 3 and 1, right? Negative 3 and 1, and then you realize that negative 3 actually doesn't work. Okay, negative 3 doesn't work because look, does it satisfy the original equation? No, right? Because when you're taking, remember the log is only defined on positive numbers, right? So from the get-go, right, from the very beginning, you're assuming that x is bigger than 0 and that x plus 2 is also bigger than 0. Okay, right? So like that condition has to be propagated down with the equation, right? This is true, but we're x and x plus 2 have to be bigger than 0. In other words, x has to be, so this one says x has to be bigger than negative 2, but anyway, x has to be bigger than 0. Right? So x has to be bigger than 0, and right, so we know that this one is out. Okay, so this is one of those things where you have to keep track of the implicit assumptions. Okay, so otherwise you'll end up with solutions that are extraneous, so-called what the book calls extraneous solutions. But really, it's keep track of your implicit assumptions. Okay, so yeah, so this is kind of nice, right? We've got some expressions like this, and we can use properties of the log to combine them and then change them, use the exponential function to change them into kind of more standard equalities that we've seen before. Let me note that the book also gives some problems like this. Natural log of x squared equals 2 natural log of x. And this is actually not something where you would try to exponentiate both sides or anything like that. Okay. This is I don't think this is actually a good kind of problem to include, but what this is it's actually basically a disguised quadratic equation. So some of the problems in the homework are these disguised quadratics. So you say, oh, instead you say, look, let's let y be natural log of x. So let's put a different name on natural log of x, and then you realize that this thing is is y squared equals 2y. Right? In other words, it's y squared minus 2y equals 0, right? So y minus 2 equals 0. So y could be 0 or 2. Right. Okay. At that point, we bring in the exponential function itself. So what we have is that natural log of x is 0 or 2, right? So that tells us that e to the 0 is x, right? So let me do it this way. Natural log of x is either 0 or 2, so x is either e to the 0 or e squared. Right? You exponential, you raise everything, you pump everything through the e to the x function. Okay, so x is going to be 1 or it's e squared. Okay. So the only part that's directly relevant to what we're talking about is this last part. Okay. The other thing that's going on is just this trick of having sort of a disguised quadratic. And so you say, oh, look, this thing is something squared. Similar problem. Basically, same sort of problem. E to the 2x plus 2e to the x plus 1 equals 0. Okay. So it's kind of a it's a fake. You think, oh, should we apply the natural log? But no, this is again a disguised quadratic. Right? So you see that this one is, this is something squared plus 2 of that something plus 1. Right? So it's, if we let y equal e to the x, then this is y squared plus 2y plus 1 equals 0. Right? And then you go on from there. Okay, so I think this is just maybe the author was running out of problems or something, decided to add this sort of problem. Couldn't come up with other problems. Okay. Okay. Yeah. So there's one warning. So let me give a cautionary example. So cautionary example. So e to the x minus e to the minus x equals 1. Okay, so this is something, again, something from the book. One way you could deal with this is to multiply everything by e to the x. So we're going to multiply both sides by e to the x. We get e to the 2x minus 1 equals e to the x. So multiply by e to the x. Okay. And then you see we're back in the quadratic case again. Okay. So then we get e to the 2x minus e to the x minus 1 equals 0. Okay. And then we play the same game as here. We'd say, let's let y be e to the x. You get y squared minus y minus 1 equals 0. And then using the quadratic equation, you get y equals 1 plus or minus the square root of 5 over 2. Okay, so e to the x equals 1 plus or minus the square root of 5 over 2. Okay, but in this case, if you use the minus sign, you're going to get a negative number because square root of 5 is like 2.2 something, 2.26 or something. So only the plus one is going to be valid for us. Yeah, Vivi.
Could you just explain how you got from there?
From here to here? From here to here?
Yeah, from there.
The quadratic formula. The quadratic equation. Negative b plus or minus, negative b plus or minus the square root of b squared minus 4ac over 2. Just a quadratic equation. Yeah, so 1 minus square root of 5 over 2 is less than 0, so impossible solution. Right, because from here you would take the natural log of both sides and you get x equals the natural log of this thing on the right. But you can't take the natural log of a negative number yet. Okay, so later on when you go higher in math, you'll learn that you can take natural logs of negative numbers. You can actually do all sorts of crazy things. You can hit e to the something. So e to the something could be a negative number. E to the something could be, complex numbers. All sorts of things happen later on. I'm tempted to get into it, but because you can actually connect this to Alice in Wonderland. No, Alice Through the Looking Glass. The book Alice Through the Looking Glass is based on the complex version of the square root function. Anyway, maybe I'll talk about it. No. In any case, yeah, this is for now an impossible solution. Okay. Yeah. Charles Dodgson, right? Lewis Carroll was a mathematician, actually, and so he encountered this thing. He knew about this thing in mathematics called a Riemann surface, and thought, oh, this would be a good idea for a story. I've only got 3 minutes, so I'm gonna tell the story. Okay, so so there's a way of there's this thing called a Riemann surface. So this, you don't have to know this at all. This is just for entertainment. And so you've got the complex plane, right? Like the real numbers, the imaginary numbers, and the combinations of them, right? And so you've got the square root function, which gives you back another complex thing, complex number. There's kind of an odd thing that happens, which is that as you walk, so this isn't going to make much sense, but as you take values going like this around of the square root function, the complex square root function, when you come back to here, you actually end up with different set of values, which is the negative square roots, right? When you take a square root of something, there's a positive one and there's a negative one. So, but oddly, as you circle, if you go around this thing in the middle, this what's called a pole in the middle, a singularity in the middle, when you come back to here, you find that the values you've got are the negatives of the ones that you had before. And if you walk back through it like this, then you return to the original values. Okay, so this gives rise to a kind of construction where you take two copies of the complex plane and you make a cut here, and you make a cut here, and you say, okay, whenever I pass through this cut, I come to here. Okay, and whenever I pass through this cut again, I come back up here. Okay, so that is the domain, the natural domain of the square root function is this sort of combined surface. This combined surface, so that when you walk through here, you end up in this world, and when you cross through the cut again, you end back up in this world. So this is like the natural domain of the square root function, the complex valued square root function. So you can see that this is the looking glass, right? You walk through this, you're going around in your normal world, you pass through this thing, and you end up in a world where everything is weird, like the negative numbers, you've got the negative result of what you had before, right? Things are just backwards from what they are in reality, right? And the only way to get back to your real world is to pass through that looking glass again. Okay. And so this is the idea of Alice through the looking glass and the matrix, right? Which, right, the descendant, right, in the matrix, the main character passes through a mirror, right, to get to the real world. Yeah. Okay, see you guys next time.